All right, today, lecture 17, homework 10 is due Tuesday after spring break. Just one note on that. I think on the previous slide, previous lecture on Tuesday, I said it was homework 9. It's actually homework 10. Not that that matters significantly, but if you're keeping track, it's homework 10. And these questions are not too difficult, but get started on it. Get it done before you leave for spring break, and then you just don't have to worry about it at all while you're gone. That'll be a nice thing. So today's lesson is actually pretty fun. We start talking about perpetual motion machines, and so a lot of this is fun information. It's interesting because you'll start seeing it a lot more in everyday life, these instances where people are claiming to have some device that does this miraculous thing, and really it's violating either the first or second law of thermodynamics, sometimes both. So it's nice to have that knowledge and be able to recognize that, because we do see things in the world a lot of times that seem too good to be true, and it's kind of cool to know why they're too good to be true and to be able to hopefully explain it to other people in a sensible, kind way. So we'll talk about perpetual motion devices and also reversible versus irreversible systems. And then we're just going to briefly touch on the Carnot cycle and the principles of the Carnot cycle, but after the break, after spring break, we go really in depth into the Carnot cycle, because the Carnot is an idealized version of heat pumps, heat engines, and refrigerators, and it gives us the best case scenario for these particular devices. So when we look at the Carnot cycle later on, we'll see actually the limitations of these devices, meaning that if it's a perfect device with no irreversibilities, we'll see what is the maximum coefficient of performance or the maximum thermal efficiency that we can ever achieve. So it's interesting to look at, and we'll just touch on it today, but after the break we'll get into it in more detail. During the break, or you can do it before you even leave, this is a bonus extra credit assignment. So this will be worth up to 10 quiz points, so it counts as a full quiz. And it's because it's bonus, it won't count against you if you don't do it, but it can help you if you do it. And I want you to take a photo of a green energy or an alternative energy setup. So this, there are many examples. A lot of businesses and industries now are starting to implement it for cost-saving measures. So I've listed several examples up there. There's a myriad more examples that you can see, and I would like to see if you can find something that's unique and interesting, especially if it's somebody or a company using something in the local area. But you must be in the photo, so I don't want you to just go on the internet and grab a photo of a wind farm and say, I saw a wind farm on spring break and here it is. No, that's not going to work. You need to be in the photo so that I know that you actually witnessed it, you saw it, you found it, you went out and searched for it. So again, this is all bonus points. And then you submit a one-page write-up discussing the energy setup. So if there are any interesting details that you know, that possibly whatever company it is has some facts on their website about what they're doing, or if you know or can look up information about solar panels or solar arrays in general, then just do a one-page write-up that has some interesting details or facts about it. And then I want you to also include your opinion. So is this a good thing because XYZ, or I really think clean energy is terrible because XYZ, you know, opinions, you're entitled to say whatever you want. Just have details and facts to support whatever opinion you give. And I will grade for content as well as grammar, so please, you know, be mindful of that, I don't want anything that's written in text type. I have had students in the past submit write-ups to me with like you are instead of your, and I just want to throw it in the garbage and not even look at it. Just that's my honest assessment of things that are written that way. So part of your job as engineers is to be able to communicate effectively, and I expect that in this class as well. So any questions on this extra credit assignment? Okay, so 10 quiz points, that's worth more than homework points. Obviously we have fewer quizzes in the class, and I think quizzes are where people can use a little extra help. So there you go. So again, the laws of thermodynamics. We have to satisfy both the first and the second law. And we naturally have energy transfer that occurs in a certain direction. So the second law enables us to identify more readily whether or not a process is a real process, because it may satisfy the first law, meaning energy is balanced. Yeah, okay, in equals out. But if we're flowing contrary to the natural direction of energy flow without adding any work to the system, then it's an impossible process. So in many cases, the perpetual motion devices or the theoretical machines that a lot of people present, they work from an energy balance standpoint. They satisfy the first law. And so it's a little bit more difficult to understand right offhand why something like that can't work. But if we're also looking at the second law and understanding that energy has direction, then it's a little easier for us to look at those things and understand. So heat engines are that was the answer on the first part of the quiz. It's the necessary device in order to take heat and convert it to work. So they always operate between these temperature reservoirs, and they always have an efficiency that's less than 100%. Heat pumps and refrigerators are used to reverse the direction of heat flow. So it requires a work input in order to take heat from a cold space and put it into a warmer space. So essentially we're making heat flow uphill or upstream, and that it requires work in order to do that. The thermal efficiency for a heat engine tells us how much of that heat we can possibly convert to work, or how efficient or effective it is at converting heat to work. It's always less than 100%. In many cases, it's closer to like 30% for real processes. And then refrigerators and heat pumps have something called a coefficient of performance, which is slightly different. But again, if we're thinking about the base definition of efficiencies and performance markers, it's the desired outcome over the required input. So if the desired outcome is to put heat into a hot space, like it would be for a heat pump, then we use QH over the work in. And if the desired outcome is to remove heat from a cold space, making it colder, then it's QL over work in. And a coefficient of performance is most often greater than 1. In fact, if it's less than 1, it means we're doing worse with our cycle than we could if we just let the energy or just converted all of the electricity into heat, as in the case of a heat pump. Perpetual motion devices, sometimes also called over-unity machines, are those that violate either the first or the second law. And so because real processes have to satisfy both the first and second law, any device that violates them will be called a perpetual motion machine. And if it violates the first law, meaning it's somehow getting more energy out of it than you're putting in, then we call it a perpetual motion machine of the first kind, or PMM1. And if it violates the second law, then it's a perpetual motion machine of the second kind, or PMM2. So something that would violate the first law, for example, would be like if you can put 10 kilowatts into a machine and somehow you get 20 kilowatts of usable work out of it. So you're only putting in 10 kilowatts. You're not adding any additional heat, and you get a greater output. Something that would violate the second law would be like if you have some device that somehow, without any work input, transfers heat from a cold space to a hot space without having any additional work input. So as we look at some of these machines or some of these devices, we can determine if they're of the first kind or the second kind. These are some famous drawings, or this is a famous drawing by M.C. Escher, who likes to draw kind of like mind puzzles. And if you look at these pictures, like with those dice on the left, on paper, in two-dimensional format, you think, oh, that's pretty cool, you know, like you made this triangle out of dice. Wait a minute, what's going on there, right? Can that object exist in 3 dimensions? No. Okay, the same for this. So like this is a waterfall that is somehow powering itself, right? So the water comes down and flows through this paddle wheel, but then it flows uphill, although it doesn't look like it's flowing uphill until you get up there, and then falls down again, right? So that can't exist in real life. And then this little tuning fork kind of thing on the bottom, where at first it looks like it's 3 cylinders, but then when you look at the opposite end, it's actually a U-shaped bar. So on paper it works, right? It's kind of a cool little mind trick, a little illusion, but it couldn't exist in real life. You can't have something like that in 3 dimensions when you consider things in real life. So the same goes for some of these self-powered devices. There have been many perpetual motion machines proposed over time that are free energy devices that are meant to power themselves somehow without ever slowing down. So you can see, for example, like this pitcher, which is just self-refilling. Somehow it is able to, because the nozzle is smaller, the idea was that it would siphon the water from the bottom of the tank and then just keep adding it to the tank there. Well, we know with hydrostatic pressure that wouldn't be available to us, that the level of that nozzle would have to be lower than the level of the water. Similarly, there are all sorts of variations of these cylindrical devices that as they spin, they have some momentum generated either by arms with masses swinging or little rolling balls on the inside, where the idea is that it will keep spinning forever because the motion induces this momentum, and then the momentum keeps it spinning. But because of gravitational effects, because of friction, these may spin for a very long time, particularly if they are made to be as close to frictionless as possible, but they won't spin forever. At the moment that you try to harness any usable energy from them, they'll stop because you can't connect anything to it that would increase the friction. Additionally, they require some input to get them started. So that's a work in. So even if this device was almost perfectly frictionless, somehow we had it in a vacuum, so it was just spinning for decades, it would only spin as long as that initial input that you put into it would keep it going to overcome any frictional losses or other things like that. So there are many different videos, which are computer simulations, that also purport to show the same thing. We'll see if this link will work. Okay, so let's look at a couple of examples of the different types of perpetual motion machines, so whether they violate the first law or violate the second law. This one violates the first law, and I want you to just look at it for a minute and see if you can figure out even what's supposed to be happening in this particular device. Right, right. Okay, so we're using, we can look at this as just like a regular heat engine, right? So we have a turbine and a pump, and we're pumping water through this boiler, and somehow we have to heat up the water in the boiler. So the idea is then, okay, well, instead of using fossil fuels, why don't we just tap into the generator to heat up the water in the boiler so that we don't have to use a secondary furnace or burn anything or cause pollution? So we can just use the energy that's created by this cycle in order to heat the water in the boiler, right? Sounds great, doesn't it? Okay, so what happens if we draw a system boundary around this whole thing? What do we have? Let's do an energy balance on it, right? So work in minus work out, Q in minus Q out, plus work in minus work out. If it were a steady state system, it would have to be equal to 0, right? So we're looking at it as a closed system. There's no mass crossing the boundary. So what do we have? We have a Q out and a work out. So what we're saying is negative Q out minus work out is equal to 0. Okay, how does that work out? Negative Q out is equal to work out. No, I mean, it doesn't balance, right? So we can't use the generator to power a resistance heater in the boiler that is used to power the steam cycle. Okay, we have to have an external heat source that is not being drawn from the system itself. Okay, otherwise all of the energy that you're using, that your generating has to go back into the boiler. But even then, when we do the energy balance, we still have this Q dot out that we somehow have to reject from our system, which means that we can't put everything from our generator back into the system and get the same amount of energy out that we did in the first cycle. So it violates the first law of thermodynamics. Then we have another steam power plant, and we looked at this example a couple of lectures ago where we just removed the condenser and decide that we don't want to reject heat to the environment. And we see that we have a power plant that receives heat from a single source and produces a net amount of work, which violates the Kelvin-Planck statement, which in turn violates the second law of thermodynamics. Okay, so it would be a perpetual motion device of the second kind, where it's just a system that cannot exist in reality. We can draw whatever we want on paper. We can design whatever we want in a computer simulation. That doesn't mean it can exist in real life on this planet, right? Okay, so that leads us to a discussion of reversible and irreversible processes. So a reversible process is one that can be returned to its original state without leaving any trace on the surroundings. Okay, so a completely reversible process is one that is reversible so that the system and the surroundings are each returned to the original state and it's like nothing has ever happened. Internally reversible means that the system can be returned to its original state. Externally reversible means the surroundings can be returned to their original state. And then totally reversible is the case that I presented at first, that the system and the surroundings are each returned to their original state, and it's as if no process ever happened. So what does this mean, and how does it apply to real life? Well, there are processes in real life that are internally reversible or externally reversible. There are very few, actually no processes that are totally reversible, but there are some that come to a very close approximation. However, those processes that are totally reversible are very idealized, best case scenarios, and in general, you can't actually use them for anything other than running experiments. That they, as soon as you try to achieve some net amount of work from them, or you try to harness the energy in some way, then you're adding irreversibilities to the system so that it's not a totally reversible system anymore. So a good example of that would be those spinning wheels with the pendulum weights, that they can be approximated as totally reversible if they're very frictionless and we don't have any wind resistance and things like that. However, the moment you try to do anything with it, then it becomes an irreversible system. You're adding irreversibilities to it. So real life is full of irreversibilities. A reversible process will provide the best case scenario. So in the case of a work producing device, you'll get the most amount of work. And in a work consuming device, you will consume the least amount of work for any process. So we still like to study reversible processes because it provides the bounds which we can design between. We can know, okay, this is the most amount of work I'm going to get out of this system. What I'm getting is this. Is that okay, or can I try to do better? And so they provide us these theoretical limits, and although we can never fully achieve a reversible process both internally and externally, we can get pretty close. And that's the idea, that's the design process, is trying to get as close to a reversible process as we can while balancing the cost of the project. Because sometimes eliminating reversibilities increases costs significantly. So what are irreversibilities? Friction is one that we're all familiar with and probably is the first one that immediately comes to mind. And friction, if you take note is that it's an oppositional force with another body in contact with another, and it leads to heat. Okay, so heat, again, is a very low quality form of energy. And in most cases, when we see irreversibilities, it's because we have heat transfer, or somehow our work is being converted into heat. Okay, the same goes for friction. So this motion, or this momentum or motion force is degraded down to heat. So we lose some of our energy process due to heat. Unrestrained expansion, so when there's rapid changes in pressure, it can lead to significant changes in temperature, which again is manifest as a heat loss. The electric resistance, heat loss. Heat transfer, it's always a one-way process, so unless we have work involved to reverse the flow of it, then it can only proceed in one direction. And then as soon as we try to reverse the flow of that heat, we automatically lose a significant chunk of our energy, because once it's degraded from a high temperature to a low temperature, we can move part of it back up using work, but we can't do it 100%. So mixing two fluids is an irreversible process unless they can be separated out again readily and easily. Chemical reactions are irreversible processes, and then inelastic deformation. So if you crash your car, right, that would be inelastic deformation, where you then now have a crumpled fender that can never be quite returned to its original shape. That's inelastic deformation. Elastic deformation would be like a bouncy ball, where you can bounce it on the ground many times and it still maintains its round shape. Some reversible approximations are necessary in design. So when we talked previously about a quasi-equilibrium process, that's one of the approximations we made early on to assume that our process was kind of reversible, or quasi-equilibrium. So if we do this process slowly enough with minimal friction, then we can approximate it as reversible. And then the second law of efficiency will tell us how close our actual process can be to the one that's modeled by a reversible one. So if we look at it in the reversible case and then we calculate our second law of efficiency, we'll see how close we can possibly get in real life. So the classic example is for a quasi-equilibrium process would be moving a moving wall. If we move it slowly, the water level just rises slowly. But if we move that wall quickly, expand and compress too rapidly, then the water begins to oscillate, and so it becomes an irreversible process, because now we have these momentum forces that are causing our motion to be less efficient. Heat transfer processes are always irreversible, but as the temperature difference goes to zero, it becomes more closely approximated by a reversible process. So if you're transferring heat from a body at 20 Celsius to another body at 20 Celsius, then it can be considered reversible. However, very few systems in real life have infinitesimal temperature differences where heat transfer is concerned. So it's a good approximation, but in practical analysis and design, we don't often encounter that in real life. So we can do our best, and we can say, okay, maybe our process is not totally reversible, but we can say that we don't have any irreversibilities inside the system. Our piston is a frictionless piston cylinder device. Or we can say there's no irreversibilities outside the system, that there's no external momentum forces or things like that. So again, we're making approximations both to simplify the analysis, but also to show us the best case scenario, and also to have us take special note of the things that we can work on. So if we make a reversible approximation and then we run our real simulation or a real analysis and we see that we have all these differences, then we can say, okay, we assume there was frictionless. Where's the friction in our design, in our system, and how can we reduce it so that we can get closer to these values? Which leads us to an idealized reversible cycle. So the Carnot cycle is one that is often used in design and analysis to give us our best case scenario. of a heat engine, heat pump, or a refrigerator. And we first talk about it as a heat engine. So from state 1 to 2, we add heat from a source at T sub H, and then because we're doing this, we maintain the temperature as constant during an expansion process. So state 1 to 2 is reversible isothermal expansion, means that the temperature is constant and it's expanding, so the volume is getting larger during that process. State 2 to 3 is reversible adiabatic expansion. So adiabatic means that there is no heat transfer. So we're continuing to increase the size of our volume. However, we're not adding heat anymore, so the temperature will be allowed to drop. So this T sub H goes to T sub L. State 3 to 4 is reversible isothermal compression. So again, we add some heat to, or we remove some heat from the system as we compress it so that it maintains a constant temperature, T sub L. And then state 4 to 1 is reversible adiabatic compression. So we no longer allow heat transfer to occur, and as we compress our system, our temperature goes back to TH. So we're returning back to our initial state, state 1. It's a 4-step cycle. So there's 4 different processes involved in the Carnot cycle, and as dictated there. So if we look at the Carnot cycle on a PV diagram, we can see 2 different possible cases, the Carnot cycle and the reverse Carnot cycle. The Carnot cycle is what is used to model heat engines, and then the reverse Carnot cycle, nobody changed that clock after, okay. The reverse Carnot cycle is used to model heat pumps and refrigerators. So you can see what it looks like on a PV diagram, and if you remember from previous discussions and from the exam that the work under, or the area under the curve on a PV diagram is the work for the system. And in this case, because it's a cycle and we return back to our initial state, it's the area encompassed by all 4 parts of that cycle that give us our net work out or our net work in, depending on which direction the cycle is operating. So you can see how Q sub H is added from state 1 to 2. And that line is not a linear line. It's an isothermal compression, usually of an ideal gas. So it has this logarithmic relationship between pressure and volume. So the Carnot cycle becomes very important to us in the next couple of weeks. It's one that we use in order to provide best case scenario, but it's also the start of using these property diagrams to look at cycles from a holistic viewpoint and say, okay, if I look at what's going on in this system, if I plot the points and the process path, then I can get a better view of how my system compares to other similar processes or similar cycles. That using these diagrams is very key and important in that way, and knowing how to plot it is important. So if you had trouble on the exam figuring out how to plot the PV diagram for that the exploding tank problem, then you really want to take a second look at it and make sure that you understand the fundamentals behind it. So looking at what's constant, looking at what changes, whether or not you have heat added, whether the volume's increasing or decreasing, and being able to plot something like this for yourself. So there are some principles that are associated with the Carnot cycle. The first is that the efficiency of an irreversible heat engine is always going to be less than the efficiency of a reversible heat engine operating between the same 2 reservoirs. So if you have an irreversible heat engine and a reversible heat engine and they're operating between the same temperature difference, the reversible heat engine is always going to have a greater efficiency, in other words. So that's the first Carnot principle. The second Carnot principle is that the efficiency of all reversible heat engines between the same 2 temperature reservoirs is going to be the same. Okay, which means that the thermal efficiency or the efficiency of these heat engines is no longer dependent on how much heat is transferred, but just the temperature of the reservoir itself. Okay, so we'll look at those definitions when we continue after spring break, but we'll touch on it briefly here. So there's a proof for the Carnot principle 1. It's also in your textbook. I don't think we need to necessarily go through the proof for that. But essentially, if you take an irreversible heat engine and use it to, combined with a reversible heat engine or a refrigerator, then you can find this equivalent combined system which accepts heat from a low temperature reservoir and then has a net amount of work. So you can show that it is in violation of the second law. Similar idea with the second proof. So let's talk about the temperature scale. We know how important it is when we're working with ideal gases to use the correct temperature scale, right? So if you use Celsius in a problem for ideal gas, then you get the wrong answer. And so maybe you think, oh, well, it's just important because it's some arbitrary thing. Like we've just decided that we have to use Kelvin instead of Celsius, so now this equation doesn't work because it's based on Kelvin. Well, yes and no. In thermodynamics, we have to have a scale that's independent of the properties of a substance. So if we look at water, or we look at air, or we look at orange juice or mud or whatever it is, they have different freezing points, different liquefying points, different vaporization points. That, you know, the Fahrenheit scale is based on the freezing point and the boiling point of water. The Celsius scale is the same way. But why is water chosen as the ideal fluid to base a temperature scale on for the rest of substances? So the thermodynamic temperature scale is independent of any kind of substance. It's based on absolute zero, which is the point at which all molecular motion ceases for any substance. So for air, for nitrogen, for water, for refrigerants, that absolute zero is absolutely zero for every substance. And so we have to use the thermodynamic temperature scale in that way because it's independent of whatever the properties are of any substance, that there's not some set boiling point on that scale. There's only a set zero. And so with a reversible heat engine, we're able to derive and find that the efficiency of the heat engine now is, instead of being based on the difference between these two heat transfers, or the amount of heat transfer, that it's just simply based on the temperature of the reservoir itself. So as we're using this thermodynamic temperature scale, it allows us to make this correlation using the idea of the Carnot cycle and the idea that at absolute zero all motion ceases. We can now replace Q sub H with T sub H and Q sub L with T sub L. And we'll get into this in more detail after spring break, but it's a good lead into that. So of note and important to remember, this only works for a reversible heat engine. That you can't take just an ordinary heat engine that is not claiming to be reversible and say, oh, okay, I can calculate the efficiency of this heat engine. All I need to know is the temperature reservoirs. Okay, because what you will be calculating is the maximum thermal efficiency of that heat engine if it were reversible. Okay, so do you understand, see the difference in that? That if you're using the actual heat transfer rates compared to just the temperature of the reservoirs itself, you're finding the actual thermal efficiency versus the theoretical maximum thermal efficiency. Okay, so this is often called the Carnot efficiency, using this T sub H instead of Q sub H and T sub L instead of Q sub L in that. Okay, any questions on this? Well, we do use it in real life. We use it all the time, but it's to find the maximum limit. So we'll say, okay, I know the efficiency of this heat engine is not going to be this Carnot efficiency, but I can find what the best possible efficiency can be. And as we look at this again after spring break, we'll see with utter certainty that it can never be 100% unless your T sub H and your T sub L are the same temperature, in which case there would be nothing happening because you couldn't produce work. So, so it's important to note that it is a valid approximation. However, there's that difference. So the difference between the real heat engine that you're actually building or using and this theoretical maximum based on this perfect cycle. Okay. Any other questions on that? Okay. So have a good spring break. Work on those bonus quiz points if you choose. And I'll see you a week from Tuesday with your homework. No, it's not 70.
Do you want us to email them to you or bring them to class?
Bring them to class. So there it is again, if anybody missed it. Take a picture of it or something.